The summer air monitoring project is really our first major step in trying to address some of the issues that are outlined in the JOSM, which is the Joint Oil Sands Monitoring Plan. The real objective of JOSM from our perspective is, the questions it asks are, what is being emitted? How is it being transported in the atmosphere? How does it transform in the atmosphere? And where is it deposited? And so that's what we're trying to answer. And so everything we're doing this summer is designed to, in a very comprehensive way, answer those questions, at least for the period of time that we're here. We chose two locations to locate our ground measurement platforms. Ultimately, we found this site here and Site 13 in the middle of the forest. And those two sites are fabulous because they're essentially right in the center of the oil sands region. So in every direction except the west, there's a mine or a facility, meaning that if the wind is blowing from the south, the pollutants are going over the site from one facility. If the winds are blowing from the north, the pollutants from a different facility are going over the site. So that the central location of those sites is critical to being able to understand and measure what's going on in the area.
We're standing here in the comprehensive air monitoring trailer. We have two of these installed here, and within both these trailers is air quality monitoring instruments that monitor pollutants of concern that have been identified in the region. We're monitoring everything from ozone to nitrous oxides to sulfur compounds, total reduced sulfurs, and a suite of particulate compounds as well. Right now our plan is for a 3-year program to stay here. It's going to run independently and collect data on its own, and it sends that via wireless connection back to Toronto so that we can monitor it from there.
So my group is measuring nitrogen oxides, NO, NO2, N2O5, nitrochloride, peroxyacid nitrates, and total nitrogen oxides. And the reason that's important is obviously because there's a lot of local sources of nitrogen oxides, and we're trying to quantify how many of those there are and how they transform in the atmosphere to secondary pollutants that are being made in the atmosphere. There's two components to this. So one is the major component is the emission factors. We need to know how much nitrogen oxides are being produced in the area. The second question that we are interested in is what happens to these nitrogen oxides after they've been released. So what chemistry does happen? What do these nitrogen oxides turn into, and ultimately how long-lived they are, and that determines how far the footprint, of emissions actually extends regionally.
This instrument is an OH reactivity chemical ionization mass spectrometer, and what this instrument measures is the total atmospheric loss rate of the OH radical. The reason that's important is the OH radical is the dominant oxidant of compounds in the atmosphere. So you can think of it as a detergent. It's what cleans out things like SO2, NO2, VOCs, carbon monoxide, and starts off a chain of radical reactions, which leads to other pollutants down the line. This measurement specifically is a very important measurement for model validation. One of the big gaps in atmospheric air quality models is what the actual radical reaction budgets are. You can get the right answer for entirely the wrong reason. And what this will help verify is that we're getting the right answer for the right reason and help identify any gaps there are.
In this trailer, we have instruments measuring aerosol pollution in here. Now in this trailer, we measure a different aspect of aerosol properties, including aerosol physical properties and aerosol chemical properties. So we need to be able to understand the particle sizes, what the chemical compositions are, and how often they impact this environment.
What we're trying to do is use high volume air samplers to collect particles that are in the air, and we have different instruments to collect different sized particles, as well as instruments that will collect samples, and we'll try and analyze for compounds containing sulfur, some containing nitrogen, dioxins.
The main instrument that we have is the MaxDOS instrument. So MaxDOS stands for multi-axis differential optical absorbance spectroscopy, and it's a spectroscopic technique, which means we're collecting light. So we're learning something from collecting light. So it gives us information on the vertical extent of the pollution, whereas other measurements at this site might measure a concentration. So they're a point source measurement. They tell you what's at the ground level, but they don't tell you how much is up there. So this technique will measure how much of these gases, where they are, and how much there is in the full troposphere. So all the way up 10 kilometers high, we'll measure how much is in that total column. So it's a different type of measurement than a lot of the point source measurements that are here.
When you have a ground site, it's really limited by the wind direction. So you can't fully comprehend or grasp what's going on in the atmosphere with a single site or two sites or any number of sites at the surface. You have to also measure in the vertical. And so that's the reason for the aircraft. The aircraft is like a super ground site, fully instrumented, but one that can fly in the vertical. And so we use the airplane to give us a measurement anywhere in the oil sands that we think that there is something of interest to measure.
This aircraft program is designed to really look at the emissions from the oil sands facilities. We know that it's difficult to conduct ground-based measurements because of the restrictions to access to the ground site. So we have to be able to do airborne. That's one thing. The second thing is the aircraft program can actually track the plumes as they go away from it. And last point is that we are using this aircraft to validate satellite retrieval products. And this is important because we have been using satellite retrieval products to look at the emissions from the oil sands on a regional basis. And so it's important for us to validate those results.
This aircraft is the National Research Council, NRC's Convair 580 aircraft. It is a national facility used in environmental monitoring and environmental research, as well as defense-related research. Through multi-year collaboration with Environment-Canada, DRDC, and DND, we have developed it into a well-equipped facility to do multi-research activities. So basically, it's a moving laboratory engaged in diverse research applications. And what our role in this mission is, we have a couple of wind measurement instruments. This measures three-dimensional wind. The wind speed is important, and the wind directions are important because that basically dictates where the plumes are, how they are mixing, and where they're going. So when you do want to see where the plumes are going, you want to know what the wind systems, what the wind measurements are. So it's very critical to know the three-dimensional wind to actually describe what the evolutions of the plumes. And also we measure atmospheric state parameters like temperature, pressure, and also aircraft state parameters. You want to know where the aircraft's location is, roll, pitch, what the aircraft is doing in a specific time. So we record it in this data system, and in real time we transfer this to the Environment-Canada data system.
This instrument is called an aerosol mass spectrometer. It was designed and purchased from Aerodyne Research in the States, and measures the chemistry on particles less than 1 micron in diameter. So basically what you get is a high resolution time series of things like sulfate and nitrate and ammonium and organics on the particles. So we can get an idea of, for example, the oxidation state of the particles, and that gives you an idea of the aging in the atmosphere, and that will contribute to our understanding of what's happening in the atmosphere.
The instrument that I'm working on is called a chemical ionization mass spectrometer, or CIMS for short. And it measures a subset of VOCs, volatile organic compounds, that the other two instruments behind us can't measure. And specifically, it's acidic compounds, things like nitric acid, sulfuric acid, and so on. This instrument is going to be running, and is running for the entire project, about 6 weeks or so. And it measures these things in real time, about 1 second. If you know what's being emitted, I can potentially tell you with this instrument if there are specific compounds which might be toxic to people living in the area, and also it gives us a good understanding of the chemistry in the atmosphere related to the pollutants that are being emitted from these industries.
So imagine a facility, whatever it might be, right? A mine, a tailings pond, a processing area, or the whole thing. We would essentially envision a box that goes over top of that entire facility. And with the airplane, we can measure all around the box at a series of different altitudes. So in doing that, we can measure fluxes of pollutants, any pollutants, going into the box or coming out of the box. And so if there's a difference between what goes in and what goes out, that's then an emission that we can attribute to something happening inside the box. So with the airplane, we can completely map the distribution of pollutants coming out of a particular facility and then track them back to what was it? Was it a tailings pond? Was it a plume? Was it a mine site? What's causing that particular pollutant? What's the concentration of that pollutant? What's the magnitude of the pollutant event? But you can do that for 3 or 4 hours, limited by the duration of the aircraft, the amount of fuel you can carry in the airplane, but you can't do it 24 hours a day. Whereas the monitoring sites, the surface sites, give it to you 24 hours a day, but at a point. So the monitoring sites provide you with the ground contact to the aircraft. And in an ideal scenario, you'd be doing that aircraft box, and one piece of the box would go over the ground site. And then you can take your aircraft box in the atmosphere and link it to the ground. So the two complement each other and give you the whole picture. And then ultimately, all of those measurements come back to our ability to develop a predictive capability. So we have a very, very sophisticated prediction model, numerical model, that has both weather and chemistry in it. And if the weather model shows a plume of pollutants that goes, from a source downrange, and with the aircraft, you can measure that plume as it moves downrange. Perhaps you can measure correctly the transformation of the chemicals. Then once you know you've got the chemistry and the meteorology in the model correct, well, then that predictive capability can be applied everywhere, right? All you need is the right emission sources. So that's how you tie in the aircraft and the ground measurements to the predictive capability for doing that everywhere. There's a lot of partners to make it successful. I'll start with Inside Environment Canada. When we were asked to put this project together, and we went to the scientists and said, what is the comprehensive measurement package that you need to undertake to be able to do what we're trying to do here? They said, okay, we need these instruments, and with those instruments come these experts. So we gathered the team of experts within the department, but even then, it's a finite team, you can't do everything. So the scientists in my group have in particular worked with many of the universities for years. And so we then went to those universities, and there's 6 of them, and said, we'd like you to be part of this, and would you like to be part of it? And the universities, of course, said, yeah, that's a great opportunity. And they brought their graduate students, and they brought their expertise, that niche that we can't fill. Then, of course, there's partners outside. So this measurement site is in the middle of a First Nations community, and we had to engage them. Are you interested? Would you like us to work with you? And they were like, yes. And then we came up with an arrangement. Lots of partners outside the universities. There's WBEA, right? WBEA has the measurement program in the area already for the compliance monitoring, and they do the monitoring on behalf of industry now. And they have the corporate knowledge for how to make measurements in the area and where the sites are. And in fact, the other site is a WBEA site. And the other major partner is the National Research Council. So we got into an agreement with them to undertake this project. And they are the most professional organization if you want to be flying in a safe aircraft that's experimental category. So we've flown with them for years, and they provided the aircraft, and that's a huge partnership. This is our first big foray into making comprehensive measurements in this area. And at the end of this sort of 6-week period, we'll have roughly 90 flight hours of in situ measurements in the area. We'll have 6 weeks of continuous measurements at our super site, and the first 6 weeks of measurements at this site. Both the other site and this site and the aircraft were all designed to give you a complete package. So in each of those 3 areas, we've got the complete gas pollutant mix and the complete particle pollutant mix. The immediate next steps are quality control of the data, start to publish the results, start to tell the stories that we've found here, and of course put all the data, once it's in its final form, on the portal for public distribution.